Okay. Kind of in the home stretch the last 4 weeks, so 13, 14, 15, 16, and a test 4 at the end of that, and then the final exam, and then we're done. Yeah, it's coming fast. Is anybody thinking of doing a final project for the circuit lab, doing a circuit project? Hands-on. Are you? Good. We'll talk about that tomorrow, I guess. I won't be giving your test back until tomorrow, so there's still one more person that's taking it. But you got the scores. Maybe we need to close that door, I don't know. And the scores were kind of split. There's a really strong group at the top of the class, and then some that are kind of various stages of getting caught up. So we'll go over the test tomorrow. But I did want to cover this stuff is kind of important for the lab. So we're going further into sinusoidal circuits and looking at sinusoidal steady state. Yes, and I'm recording, right? Yeah. And this is where, to me, it gets more interesting. All this stuff is important for different aspects of circuits, but I think a lot of useful applications, many applications, more probably predominantly are with AC circuits. It's just a domain. AC circuits cover like power distribution. They also cover communication systems. Just really important part of our world. Wouldn't be able to do a lot without them. And we only have like about 10 or 11 slides. A lot of this stuff is a review. Remember I said back at test 2, you're going to see all this stuff again. With complex numbers, that's what we're doing this week. We're going to be doing nodal and mesh analysis. We're going to be doing Thevenin. We're going to be doing op-amps. All these circuits that we did before with DC circuits, we're going to be doing with AC sinusoidal circuits and applying the same techniques, except we just have complex numbers. So whatever issues you had on test 2, make sure you go back and look at that and try to resolve those now. It's a chance to kind of revisit all this stuff because it's going to be all coming back at us. So the difference, though, of course, is we're not looking at resistance anymore. We're going to be looking at things called impedance, which allows us to include inductors and capacitors as if they are resistors. So as a quick summary, the impedance of a resistor is is what? R. It's just R. That was the easy one. The impedance of an inductor is J omega L, or omega L with a phase shift of 90 degrees. The impedance of a capacitor is 1 over J omega C. Is that door locked? Oh. Minus J over omega C. I guess it was open, so I didn't mess with it. Last person in gets to open the door for the next person. And then the reciprocals of these is the admittance, and these are all technically possibly complex numbers, so there's a bar across them. Admittance is 1 over R for a resistor. For an inductor, it is minus J over omega L. For a capacitor, it is J omega C. And so the procedure that we follow in solving sinusoidal circuits in the steady state, meaning after any transient has died down and you just have the sinusoidal oscillation, is we transform the sinusoidal time functions to phasors. We convert every element in the circuit to a complex impedance and admittance. We apply all the network reduction that we learned from DC circuits using these complex phasors to determine the desired response in phasor form, and then convert back, if you need the time function, convert back into the time domain with an inverse phasor transform. So it's really just DC circuits all over again with a little bit of twist with complex numbers. So an example of nodal analysis, dependent sources are going to come back, you know, they're all coming back. So we got to get on top of those things that were messing us up before. We have to convert this circuit into the phasor domain. This is a circuit with a sinusoidal excitation, and we have inductors, we've got capacitors, we have sinusoidal sources. So we convert this into the phasor domain. So the first step is, well, this source, what is this, the phasor form of this source? In the phasor domain, this source is going to be called what? 20 angle. Yeah, 20 angle 0 degrees. The omega is 4. So the, I think better not hear any tinfoil crinkling. The inductor has an impedance of J omega times 1, and since omega is 4, that's going to be J times 4. The capacitor has an impedance of minus J over omega C, and this is omega times 0.1, so that's going to equal minus J, what's the 4 in there, minus J of 2.5. This inductor here is going to be J times omega times 0.5, which is going to be J2. Okay, so this becomes our circuit, and we redraw it in the phasor domain. So we're asked to find I sub x using nodal analysis. We're going to solve for capital Ix, the phasor of that complex phasor of Ix, little ix. And we have nodal voltages. We can call these phasor V1, phasor V2. Everything works just like it does for DC circuits. So we do nodal for V1. And the V1 node, remember this, it's going to be the currents going into that node are going to add up to 0. So we're going to say 20 angle 0 minus V1 over 10 is that current going through there, and then plus 0 minus V1 over minus J 2.5, that's the current going up. That's this current. And plus phasor V2 minus V1 over J4. Has to add up to 0. Okay, David, you're it. If anybody else comes in, you have to open the door. Yes, question?
0 minus V1 over 2.5 minus 2.5J actually Ix, right?
Yeah, what's minus Ix?
Yeah, minus.
Mm-hmm. It's minus Ix. So Ix, well, let's do nodal for V2. Nodal for V2 is V1 minus V2 over J4 plus 2ix as a phasor plus 0 minus v2 over j2 equals 0. So this was our first equation. This is our second equation. And our third equation is that ix is going to equal v1 minus 0 over minus j 2.5. So you now have a system of 3 equations of 3 unknowns you can solve in free mat. And we're going to be doing that tomorrow in the lab. So it's just kind of more practice in the computational part of this. We solve 1, 2, and 3. Going to give us that V1 is going to equal 18.97, angle 18.43 degrees. V2 is going to equal 13.91, angle 198.3 degrees. And Ix is going to equal 7.59, angle 108.4 degrees. So this is the thing we are interested in. This Ix can give us the little ix of t, which is what we're trying to find, meaning it's going to be 7.59 cosine of 4t plus 108.4 degrees. Amps. So that's showing you the whole process for the AC sinusoidal analysis. That's what we do. 170? Pardon me? Solve 1, 2, 3. That's going to be just solving the systems of equations. And yeah, so that's going to be in free mat. We're going to show how to do that tomorrow. So yeah, there's some extra tools in free mat that are going to make it easier to work with than just doing the plain commands. We're going to have a couple functions that will help us. In fact, I just downloaded them, so I could probably do some of these pretty quickly. I don't know. You're interested in seeing? I can show you now if you want to. I want to see how it works in free mat. I'll probably make a mistake though, so I'll wait until tomorrow. And of course, remember that nodal analysis with voltage sources is going to bring up those things called supernodes, which you're going to run into sometimes. That's when you have a floating voltage source. Remember, case 1 of nodal analysis with voltage sources is that that is the easy way. That's case 1 is where the voltage source is connected to ground. Okay, so that's like this guy right here. Those are pretty easy because we know this node voltage here is 20 angle 0 degrees, right? It's the easy one. But what happens if you get a floating voltage source? That's case 2. It's not really hard, but it's not as easy. Vs is between 2 non-reference nodes. And that's what we then decide to make a supernode. And an additional, so basically do KCL, for the whole supernode. And an additional equation which we get from that voltage source by inspection. Right, so that's where, if you have sort of like a V3 and a V4, you know, something like that, right? Where there's a circuit and other stuff here, and you know, this is a V4, that's a V3. The bi-inspection equation. Who wants to try the bi-inspection equation? Really easy. Isaac, you want to do the bi-inspection equation? Yeah. Yep. Like V3 minus V4. What about it? Yep. It's constrained by that voltage source. That's the bi-inspection equation. So you're going to get those. Okay, now, Isaac, I'd like you to tell us what this means to you. Without talking with food in your mouth. No, I'm just giving him a hard time. So, so mesh analysis is the other one, right? You haven't forgotten mesh analysis. How could you? So here's the circuit with mesh analysis. We're asked to find I0 using mesh analysis. I0 is the current coming up from the voltage source. And you can see that there are 3 mesh currents labeled for us, I1, I2, I3. And you can start with the 1, I2, I3. Yep, you can start with the I1 mesh. And I'm going to do that down here, I1. The I1 mesh says that 8, where are we here? 8 I1 plus J10 times I1 minus I3 minus J2 times, anybody? I1 minus I2, good. That has to equal 0. The, Isaac, yeah. What's the difference between mesh and nodal versus KVL and KCL? Yeah. So mesh is based on KVL, and it's based on KVL. It applies KVL in a very systematic way. Nodal analysis is based on KCL, and it applies in a very systematic way. KCL is just really you can apply KCL anywhere, but if you apply KCL to these so-called node voltages that we describe relative to some reference point in your circuit, that's nodal analysis. I2 is, we've got a bunch of J2s there, so we're going to start up with the bottom one, I guess. So minus J2 times I2 minus I1. Minus J2. You know, we would be saying plus, except there's a minus sign in front of these things because it's a minus J, right? So plus times minus J2 times I2 minus I3. Plus 4I2 equals 0. Oh, but there's one more thing. Plus 20 angle 90. All right. Plus 20 angle 90 equals 0. That's your I2 mesh. And then your I3 mesh. Anybody want to handle the I3 mesh? We're not doing it? Why? Current source there, that means what? Super mesh? Ollie, does it mean super mesh? You don't know? I3 equals to what? 5 angle 0, yeah. That's the current source in an outer mesh. And then you can use that to substitute out one of these variables. So because it's really sort of by inspection, right? You can get rid of that one and that one. And IO is what? Yeah. IO equals minus I2. Now, so you can see some of the circuits have already been converted into the Phasor domain for us, right? This one already has been, all the components are complex, and the sources are in Phasor form. So that will also happen just to kind of speed up the time. You'll have circuits in both situations to kind of deal with, but likewise, the super mesh is when you have a current source between meshes. In that case, the super mesh is the recommended approach. And so that's a situation where you have, got like an IA and IB, and there's some current source here, which is say 8 angle 30 degrees. So you have to do, so you do a super mesh equation plus another equation. From the source. Inspection. And to help us with that equation today, we're going to have Alex. What is that equation for this particular case? If we have an IA and an IB and an 8 angle 30 source pointing up, what would the by inspection equation be for the super mesh? So the whole equation is what? Okay, does everyone agree? Sound good? Mason, what are you saying? Is it the opposite of the sum? Yeah, this is not the way I normally do it, Alex. What I normally do is I say, well, this arrow is going up, right? And this arrow has to represent the net current flow with IB it's going along in its direction and IA going against it. Now let's see what happens here. So I don't know, what I do is I say, well, that means, I see this and I say IB minus IA, it has to equal a net of 8 angle 30. So I think I agree with Alex. I think I says, is that right? Or well, no, wait, it's IB minus 8 angle 30. Wait, what? So I say IB minus IA has to have a net of 8 angle 30. So therefore, IA equals IB minus 8 angle 30. So it's a little tricky. Your approach actually was kind of, why doesn't that approach work? You're saying that the current going down 8 angle 30 has to add up to, that current going up, which is, the current going down is IA. So to 8 angle 30 plus IB. I think the point is the net is that 8 angle 30 is the net, right? And that has to be, that's composed of the net combination of IA and IB in the correct relationship of the signs, yeah. So it's this one here. But actually, you know, I don't even write it that way. I just write it as, we know the net is this one. That IB going up minus IA going down has to result in 8 angle 30. Okay, questions? Superposition is another really nice technique that we learned in DC circuits. And in this case, it can actually make sense where you might have a circuit with sources at different frequencies. So here's a circuit that has a DC source, a source going at 5, omega of 5, and a source, a sinusoidal source with an omega of 2. You would not be able to solve this with one Phasor transformation. Why not? Why can't you solve this with a single Phasor transform? A 5 volt can't be turned into a Phasor, a DC source. Yeah, how come we, why cannot we, could we solve this with a single Phasor transform? Could we transform this circuit into the Phasor domain and solve it and transform it back? Well, we can't. Why not? Yeah, the frequencies are all different, right? And when the frequencies are all different, that means we have a different omega for this source versus this could be like omega 1, have an omega 2, and this is an omega 3 really, which is 0. And that affects the impedance of all these devices, right? So, you know, this is J omega L, but it's omega 1L when this, with the effect of, its response to this sinusoid is going to be omega 1L. The response to this sinusoid is going to be J omega 2L, and the response to this one is going to be just, well, what is the inductor? It's a short circuit, right? It's just going to be 0, omega 0. So, so we can't just do a single Phasor transform, but we could turn off those sources and turn them on one at a time and solve for each one in the Phasor domain separately at different omegas, right? So, so that's where superposition is pretty good, because superposition just says you can solve it independently from each one, then you just add those results together for the total net. And so we can say with the DC source on, and with the DC source on, and the other two turned off. You already have the circuits. We already got the circuits here. Right? That's the DC source on, and the other two are turned off. What is V1 going to be? One, 1/4. Sorry, I can't hear. Can you say it louder? It's going to be 1. It's going to be 1. Actually, it's going to be -1, right? It's going to be minus. It's a voltage divider, right? 1 over 4 plus 1 times 5. It's going to be -1 volt. Right. The voltage V1 for that 1 ohm resistor is the minus sign is kind of on the high potential side, so it's going to be negative, right? Losing energy over there. The minus current is sort of flowing in the minus sign, coming out the plus sign. That's active sign convention. So we have a negative voltage drop there. With the AC voltage source on, let's see, AC. With the AC voltage source on, we have, the Phasor transform, that's 10 angle 0. We also have this 2 Henrys, this J4 is going to be J times 2 times 2. Omega's 2, and the number of Henrys is 2. And we have this minus J5 is this is going to be minus J over, and what is the 0.1 is going to be J over 2 times 0.1, so that's going to be minus 5J. And we got a 4 ohm resistor there, and we're asked to find V2. The trick we're going to use is we're going to combine these. Find the equivalent impedance. This is going to be 4 times minus J5 over 4 minus J5. That's the equivalent impedance of that parallel combination of a resistor and a capacitor. And at that point, we can use the voltage divider equation. We've got 3 impedances now in series. We've got the J4, the 1 ohm, and this parallel combination. So the voltage divider equation, I think I want to go back to red here. Is going to be, well, it's 1 ohm, so it's going to be 1 over, and then we're going to do our J4. J4 plus 1 plus this parallel combination, 4 times minus J5 over 4 minus J5. And all that's going to be times 10 angle 0, the source, and that's going to end up equaling 2 point, this is V2 by the way, sorry, V2 equals 2.498 angle of minus 31 degrees. So that's V2, and then we have to find V3. Mason.
We have the combination of makes J20 divided by 4 minus J5. The only way to handle that is to multiply top and bottom by 4 plus J5. That's the way I saw it in the book. Question
is, how do you simplify 4 times minus J5 over 4 minus J5? Is the only way to multiply top and bottom by 4 plus J5. That's the complex conjugate. Yeah, that's the way you do that. So you can get a real denominator. You would have to do it to solve this problem. I mean, yes, if all you have is a calculator that can only do that kind of stuff, yeah, you would have to do it that way. But if your calculator can handle complex numbers, it might be able to do that for you. If you use free math, you don't have to do that either. You can get away with a lot of stuff. But you should know how to do that, right? You should know how to rationalize. Is that called rationalizing? Rationalize that thing. So I don't know. It's making it real. Make the denominator real and just put the imaginary part, complex part on top. That way you can add them together rectangularly. Yeah, Matthew?
The 10 cosine 2t to the 10 angle 0. I guess I kind of got it.
10 cosine 2t to that is, remember this is Vm cosine of omega t plus theta, right? And when you express your sinusoid as, you know, Vm cosine omega t plus theta, then this is going to be Vm angle theta. And since there isn't any phase, it's just the omega t in there, theta is 0. So it's just 10 angle 0. Now with the sine, it's tricky, right? So for the third one, this is why this becomes 2 angle minus 90 degrees. With the sine, remember we found the sine of 0 degrees equals cosine of what? Sine of 0 degrees equals cosine of what? Draw a picture. Here's sine of 0 degrees, go like that, equals what? Cosine of what? Pi over 2? Well, let's say cosine of pi over 2 is going to be this point here going down, right? It's negative pi, it's right. You're going to have to make that transformation sometime, you know. So if this is confusing, ask again. Sine of 0 degrees is the same thing as cosine of minus 90 degrees. And what that implies is there's a 90 degree phase shift between the sine and the cosine. This is how you get it right. If you change this to say sine of theta plus 0 degrees is going to equal the cosine of theta minus 90 degrees. Some offset theta should give you the same, right? And that means sine of theta becomes cosine of theta minus 90. And you can, if you're not sure, you can check that out with your calculator. Prove that to yourself. So in this case, sine, we have 2 sine of 5t, and that's going to turn into 2 angle minus 90. Right, so 2 sine of 5t is going to equal 2 cosine of 5t minus 90 degrees. And so again, this becomes the Vm, and this becomes the theta. So that means in the Phasor domain, that's just 2 angle minus 90 degrees. Okay, that's important. So when you see a sine, if you just have sines in there for all your sources, you can just do a regular Phasor transform and it will all work out the same. But your answer will have to be expressed in terms of sine. But if you have a mix of sines and cosines, you'll have to turn the sines into cosines so you can do the Phasor transform properly. Okay, so this third one is a little trickier. We've got a current divider situation going on here, don't we? We have to find V3, which is going to be I1 times 1 ohm, right? So V3, and if you're really lazy, you can write this all out as one big formula and then deal with that later. I'm going to give myself a little more room here. So it's a pretty big operation here. I'm going to erase this. So, oops. So, here. Oh, can't get rid of that. Weird. So anyway, so V3 is going to equal. It's going to equal 1 ohm times I1, and that's going to equal. It's pretty messy, right? Remember the sum of the reciprocal of the sum of the reciprocals. So I1 is going to equal, well, let's first look at this thing. We're going to have to combine this guy, and this is going to be 4 times minus J2 over 4 minus J2. Now the current divider formula says, I1 is going to be, remember the current divider equation says I1 is going to equal G1 times IS over G1 plus G2, where those are the conductances. But now these are the admittances, the reciprocals of the impedances. So it's going to be, this is for finding I1. So this is going to be 1 over So the G1 is going to be the impedance of the path that I1 is going through all the way from the top part of that current source to the bottom side of that current source, right? And the impedance of that path is going to be 1 ohm plus this combination 4 times minus J2 over 4 minus. So we say, okay, it's 1 over 1 plus 4 times minus J2 over 4 minus J2. Then we got to do the sum of G1 plus G2. Well, G2 is this path over here. This G2 is J10. So we're going to say 1 over J10 plus this 1 over 1 plus 4 times minus J2 over 4 minus J2. And all that times 2 angle 90, minus 90. Because that's times the current source. Okay, so this is the I1. And is it readable? Do whatever you need to with parentheses to kind of make sure you can see that. Okay, so that's our V3. It's going to be 1 ohm times this I1, or 1 ohm times all that. And once you boil that down, you're going to get V3 equals 2.328 with an angle of, looks like minus 80 degrees. Or maybe it's 81. Close enough. Anyway, so the total VO is going to be our total VO, which we're trying to find. What is this voltage here? Our total VO of T is going to be the sum of all these three parts, right, from superposition. It's going to be minus 1 plus 2.498 cosine of 2T minus 31 degrees plus 2.328 cosine of 5T minus 80 degrees. Okay, so that is the superposition. Isaac? Yeah, the superposition allows it to solve each part of that separately, each part which is working at a different frequency separately, and then adding the total results together. Superposition is why communication systems work, why we can have, you know, the frequency spectrum has people transmitting at all kinds of different frequencies. Total spectrum is the sum of all those, but if they're band limited, they can sort of filter out the stuff we want. We can, you know, add those things together. It's all very cool. A lot of things are made possible because of superposition. Isaac, yeah. Other time constraints. Well, these are steady state solutions, sinusoidal steady state. And sinusoidal steady state is long after any temporary startup transient has died off. Like when you first turn on these, if you come to your bench in the morning and you turn on these sources, you know, maybe you're turning on the 5-volt source before you turn on the 10 cosine of QT source a little bit. Eventually, everything's going to kind of stabilize, and any transient that was starting off, you know, when you turned on the power is going to go to 0, and you're going to be left with this solution right here. So this is sort of like for t kind of like much greater than 0. It's not the transient like we've been doing for first and second order circuits. It's not that thing that dies out. It's just this steady state. It's long after the transient has died out. Yeah, it's a good question. Okay. What about source transforms? We have 4 minutes. We don't have to do any source transforms. We can just look at them. Remember, source transforms are how a voltage source in series with a resistor can turn into a current source in parallel, and the same thing works with impedances and phasors. So that's the same. So you can do those if you need to. What about Thevenin's theorem? Oh no, yes, Thevenin's theorem says any linear two-terminal circuit can be replaced by an equivalent circuit of a voltage source, phasor, in series with an impedance, where the V Thevenin is the open circuit voltage at the terminals, the open circuit phasor voltage, and Z Thevenin is the equivalent impedance with all independent sources turned off. Okay, and then we're asked to find I0 using Thevenin's theorem, and I think we'll probably just pick that up on Wednesday. So we can break a little bit early today for questions. Isaac. Okay. Mm-hmm. How does jumping a car work? From a physics or circuit perspective? Well, you have a battery that's kind of weak, and you're trying to start your car, doesn't have enough voltage or juice to kind of get the thing to turn over. So you hook up your neighbor's car, and it's it can be a little risky. I've heard you can kind of fry the donor car can kind of fry their alternator if the battery's like really dead. But typically the batteries, the bad battery is just kind of low. And when that happens, when your battery is low, I mean, unless you actually left your lights on all night, and you drained your battery, which can happen, you should just get a new battery. If it's just a temporary thing, you just did something bad once, it's okay. But if you're driving along, because those batteries, they're designed to last 72 months and then they die. So once they're past the 72 months, they're not coming back. So you should just get a new battery. But yeah, so you just you hook up from one battery to the other, but you're actually the hookup is not, you don't connect directly to the battery, right? Why not? Sorry? Well, the good battery is over here. The bad battery, you got the bad battery here, and what you do is, if this is the plus side, you connect the plus side to the bad battery plus terminal, but you connect the minus side to the frame of the car. Why do you do that? Yeah, but why don't you connect it? Did you connect it to the minus side of that battery? Okay. So you can connect this to the engine block. Here's the engine block, your valve covers. And you connect it somewhere where there's a big, good metal connection. Why do you do that?
Well, I know a lot of batteries in cars,
Ground is on the battery. Yeah, there is I mean, you could connect it here, but that would be unsafe because. You mean there's a ground very close to the battery? Generally, you want to make it away because when you make that connection, you could get a little spark. And batteries do explode especially when they're drained. Like if you left your car lights on all night. As batteries drain off energy, they're actually releasing hydrogen. and that can build up in the engine compartment. I don't know. Hydrogen is lighter than air, so it should go up as soon as you open the hood. But I have heard stories where people blow up batteries, and then you get a bunch of acid everywhere. Yeah. Jump in a car in a closed garage. So you're sometimes you have to rev the engine of the source car, give it a little more power, and that will raise the voltage here. And, but actually, it's sort of like the alternator that's sort of driving the battery, which kind of then, when you speed up the car, it raises the voltage, and then you get more power over there. So anyway, you're supplementing the battery of the bad car with your battery. What if the voltage of the donor car? It would drop a little bit when you hook in the other car. Batteries do have a finite lifetime, and they're designed like when they tell you it's a 72 or 60-month battery. It's gonna go right then. You're not gonna get 80 months out of a 72-month battery. They peg that pretty well. No, you're not jumping. You're not damaging your battery. But if the other batteries like really malfunctioned, like it's a short, and you hook up your car to it, you could damage your alternator, which is charging your battery, because it might not be able to handle the current. David, do you have a question that's not related to charging a battery? No. Okay. You have a follow-up question? Yeah. Okay. Chase, if they're 12-volt systems, I can't see why that would be a problem. But like a small car, you shouldn't try to jump up a monster truck with a small Honda Civic. It probably wouldn't work. You might not have because it takes a certain amount of amps to turn those starters if the starter's turning. And a big truck like that would probably have a larger starter. No, the alternator has to the alternator is, it might be spitting out 14 volts, depending on how fast the car is turning. That's enough to get turned into the, oh, thank you. Is this all? Yeah. Actually. The cab light dot, you mean the light that burned out? Okay. Yeah. I often just, I disable those, the tar door light, because once you bring your battery, once you're like, oh, why do we even have these? I had it on mode. Yeah. Then just died. Yeah, just get a key light. Yeah.